Great. The next topic is that we're going to try to apply some of the learnings that we've made from the PVT discussion and bring that into talking about initial fluids in place. And that's relevant because it's something a lot of people, managers, investors, engineers, geologists, petrophysicists, etc., have a relationship to because it's such a key number that represents the value of a company, the remaining value of a company, that maybe the value of an asset, etc. And it's typically one of these larger numbers that you hear a lot about from different fields. So we'll see how PVT essentially impacts that type of correlation. So just a short reminder again, and I'm mentioning this a few times because I think it's important that we have good definitions and clear definitions for reservoir volumes and surface volumes specifically. So again, when we talk about oil reservoir oil volumes, we use a subscript O, while the O hat and G hat subscripts are meant for referencing surface volume. Then originating either from an oil phase in the reservoir or a gas phase. And here we have the oil phase. So VO is the reservoir oil. In this case, surface oil is denoted by VO hat O. So surface oil originating from the reservoir oil. And then we have V subscript G hat O, which is the surface gas originating from the reservoir oil. We know that these numbers are used in how we define the formation volume factor specifically for oil, right? So we know that BO is equal to VO over V hat OO, and RS is equal to VG hat O, VO hat O, right? And this is what we need to calculate in place volumes for oil. And as you see on the next slide, we have original oil in place. But here it's important to note that we're also using the subscript O here, because we can have original oil in place originating from the reservoir oil. But as we'll see later, we can also have original oil in place originating from the gas phase, which is accounting for that condensate that is in solution. As we know very well, it's to make this calculation, we need to essentially convert this VO, which is the hydrocarbon pore volume in a single phase sense. And we, as many people that are reservoir engineers, at least they've seen this many times before, where we need the bulk volume of the fluid, we need to multiply that with porosity, and then we need to remove whatever water is there to end up with the hydrocarbon pore volume. This is then, reservoir barrels. That's the units of hydrocarbon pore volume. And we need to convert that to surface, and then that's why we're using a formation volume factor. It translates and helps us translate these volumes from the reservoir up to the surface. Since we know that the units of BOI, which we saw on the last slide, this particular guy right here is reservoir barrels per stock tank barrels, we need to divide by BOI, such that the unit is stock tank barrels. Okay, so we have reservoir barrels divided by reservoir barrels over stock tank barrels, which gives us the units of stock tank barrels. Similarly, we even for an oil reservoir, we can quantify the reserves of gas, which is given by original gas in place. I guess calculation. And here on the slide, it's actually a typo that I saw now, and that will correct immediately. That's why it's nice to have something to write over or write with. Here the so-called GO, or the original gas in place originating from the reservoir oil phase, is just equal to the oil in place from the reservoir oil phase. So this is the same guy as this up here. Then we multiply by the solution GOR, so the in situ solution GOR. It's a very simple calculation, which we again saw the definition of here. And this is where, on this particular slide, is where we see the importance of actually knowing these different different surface and the reservoir volume definitions. Great. So now we've learned essentially half of the different original oil in place and original gas in place calculations that, at least from a PVT perspective, it's necessary. Again, moving over to gas, this is probably the third time we've started to look at gas, so we should start to become familiar with that, but we reiterate on a lot of the information. So gas-related PVT properties, we know that we are only using BGD. That's what we've learned, that's the correct way of quantifying information volume factor for gas. And we know that that's the reservoir gas volume over the surface volume of gas originating from the gas phase. And the same goes for solution GOR. We know that the units of solution GOR typically is barrels per million. So we know that we need to have a surface volume of condensate divided by a surface volume of gas, both originating from the reservoir gas phase. And the key for that is seen here. Also worth emphasizing is that on some of these slides we're using an I here. The I here is just to indicate that this is in situ. This is an in situ or initial formation volume factor for gas and an initial solution CGR. And to calculate this so-called original gas in place, we simply take the hydrocarbon pore volume in a single phase sense, which in this case is only gas, is a VG. So this is also hydrocarbon pore volume here, and then we divide by the formation volume factor of gas, so the so-called tri-formation volume factor for gas, and we end up with units of scuffs. So that's very nice. And typically when we talk about reserves for gas, we're typically talking about BCFs of gas in terms of units, and not that many times scuffs, which is I guess 10 to the 10th scuffs is equal to 1 BCF, I think. Don't arrest me or shoot me. Shoot some of my colleagues, you know. But good stuff. And when we are calculating the original oil in place from the reservoir gas phase, so this is essentially the condensate, which is important because you can actually book reserves, oil reserves in even gas or even condensate fields. So we need to account for the condensate that's in solution with the reservoir gas phase, and to do that we need to take the original gas in place number from the reservoir gas phase and multiply with the solution CGR. So fairly straightforward, and now in total, just to I guess have done a little bit unsure how we do display screen. So if we just do a white screen here, just to summarize a little bit, we can say that you know, with my very good handwriting, that was sarcasm, but we can summarize a little bit. So we know for the oil side we have original oil in place from reservoir oil, and then we have original gas in place from so this is from a reservoir oil, right, from the reservoir gas phase. And then we have the same for a reservoir gas, where we have original oil in place from the reservoir gas phase, which is the condensate, and then we have original gas in place from the reservoir this is oil and reservoir gas phase. Meaning that, you know, if we, let's say we had a system that you know, where we had a gas cap and an oil rim, let's say, in a reservoir. So this is at reservoir conditions. Let's see, this didn't work very well. Yeah, there it disappeared on me actually, which was not very nice. Let's see. Yeah. So now I guess I have to do it all again, but that should be fine. So we have on the oil side, we have original oil in place from the reservoir oil, original gas in place from the reservoir gas, and then on the reservoir gas side, we have original oil in place from the reservoir gas phase and original gas in place from the reservoir gas phase. Here I hope I said reservoir oil, and I'm sorry if I didn't. So assume we have a case where we have a gas layer here and an oil rim right here at TRES and PRES. Then if we would like to calculate and book reserves, our total reserves, our original oil in place numbers, would be the total of original oil in place from the reservoir oil and original oil in place from the reservoir gas, while the original gas in place would be the sum of these two guys, original gas in place, like that. Okay, so fairly simple, and probably not the best explanation from myself, but it's just worth emphasizing. Good. So the next thing that's kind of like not a secret, but it's not that well known, is that you can actually take a reservoir gas phase and reservoir gases, and you can calculate a so-called, what we call sometimes a biologist BOI, which is a geologist formation volume factor for oil, but apply it to gas condensate reservoirs in this exact same manner. And to do that, we need to have the same units as BOI, and to get the same units for BOI with the reservoir or for a reservoir gas phase, what we then do is to take the so-called dry formation volume factor for gas and divide by this solution CGR, and we'll end up with units of reservoir barrels per stock tank barrels, which is the exact same units of as for the BOI. And typically, just to provide some ranges, the BOI, if we had a plot right here where we can say this is probably on log scale, let's say we have 1, and then we have 10, and then we have 100, then we have like 1,000 maybe, where this is reservoir barrels per stock tank barrels. On a rule of thumb basis, maybe somewhere between, let's say we're down at maybe 4 right here. We can say that from 1 to 4 maybe. So at 4 we're very, very close to the critical point. A formation volume factor of 4 would be very close to critical for an oil. And then it would transition into becoming and let's just say that this is the critical point, such that to the right of this particular curve we'll have a gas phase. Okay, so this is actually a continuous curve where the values that we typically have for BGD over this little rs would then, in this particular case, start at 4 and then go up and onwards right here. Okay, so this gas condensate BOI BGD over little rs can be used in the exact same way as we are applying BOI. So let's say you would like to calculate original oil in place for a gas condensate reservoir, then you could just do hydrocarbon per volume, and you can simply just divide by BGD over this little rs term, and you would get this volume in units of stock tank barrels. Good. So that's a little secret. Also, when we start to discuss, a so-called producing GOR, when for instance, the GOR is not equal to the solution GOR anymore, it started to rise because of the bottom hole pressure is dropping below the saturation pressure, or the average reservoir pressure is dropping below the saturation pressure, and we see a GOR increase in the producing GOR over time. the most generic way to represent that would be to include both of the phases, right? Or both of the reservoir phases. So if we have both a reservoir gas and a reservoir oil phase down in the reservoir, you have to both account for the surface volumes of gas from both the reservoir gas phase and the reservoir oil phase, and similarly account for the oil and condensate that is produced at surface as